Good afternoon. We are Team 1, and we are presenting our presentation about serious video games, simulation engine for movement. This is for the class of computational modeling of movement, and this is a presentation of the 22 October. Our team members are me, Jimena Patricia Garcia Magdaleno, and
Me, Mauricio Rafael Castillo.
talking about the introduction, we have a brief overview of the challenge, which was creating a serious video game using the knowledge that we obtained by studying the basic of mathematical motion in 2D with air and without air resistance, and we modulate our system using MATLAB as a simulation of a parabolic trajectory. About the challenge description, the importance here in Mexico is because it's a country located in a volcanic zone. Due to this, it's really important to our people to face these kind of situations, and even more to have training people or rescuers that can help in these kind of situations. That's why the importance of serious video games like our challenge of this period. Challenge stages. About sensitization, it was our first stage. It was getting to know some of the tragic consequences of volcanic eruptions here in Mexico. That's why we then investigated about what are serious video games and the importance to help people to train to these kind of situations so that people can face them in a better way in a controlled environment. Investigation, it was about we investigate the real parameters of a volcanic ejection so that we can modulate our model in MATLAB by using realistic data. For product socialization is meant to be that people gets to use it, basically that they see how it works, how they can analyze it, and kind of introduce themselves to a realistic situation of this kind.
Initial research. We researched the volcano eruptions, and we found that a volcano eruption is the expulsion of gases, rock fragments, and/or molten lava from within the Earth to a vent on the Earth's surface. Serious video games, we found that were digital applications that were meant to basically teach while doing it in an entertaining manner. So while the normal video games are just made for entertainment, serious video games are also made with the intention of teaching and being used as actual resources. Some relevant examples of these are Rails by Spectral Labs, which is used to train first responders. It uses VR and AR for enhanced realism. And another good example is Merits, which is a paramedic training for car accident scenarios that makes it so they can practice in a safe environment. For the modeling in Excel, we first did it without the air resistance. We didn't consider that at the time. We used the position with the horizontal distance traveled, the Y, which was the vertical height above the ground. The position vectors trace the parabolic path of the projectile, and then we use a formula for velocity for both for X and Y. And then we made graphs for each one of those, as well as acceleration, which was the second derivative of it. For our first model in Excel, we didn't consider air drag, so there was no air resistance to it. We used these data, which were mostly made up numbers, like for example, the angles and stuff. For this part, we hadn't yet researched what actual volcanoes angles are like, because we were just trying to get a hold of the formulas. We used the position equations to get X and Y over time. We used the velocity equations, which we used cos and sine, and we got some results such as these, which maximum height was 20 meters, and the range was 106 meters, with a time of flight of 4 seconds. Here you can see an example of the travel.
For slide number 5, we have air resistance, which was the main point of all this modulation. Why? Because we analyzed the difference between a parabola without and with air resistance. What is the main difference is that air resistance makes a simulation apparently or to be more in a realistic way, because we have a variable in the X or in the horizontal axis that gives us a lower higher point and a smaller range in X. That is really different in comparison with the parabola without air resistance, because in the parabola without air resistance we have a parabola that is almost symmetrical, almost perfect, which is not real in the real life. And while we are analyzing a real situation, a real volcanic situation, we need the presence of air resistance in our model. Those are some of the formulas that we use, for example, velocity in x and velocity in y. And all of this is based on Newton's second law. And also for our simulation, we use the Euler's method that allows us to see the trajectory of the particle in step by step. Continuing with air resistance, we have the flowchart that we use for our MATLAB simulation. This is how it works. First, we start the application, then the user introduces the parameters, and if the user doesn't modify it, we have ones that are the default ones, that those are our first data investigation about realistic volcanic data. Then we initialize the variables, and those are the formulas that we use to compute the outputs of our simulation.
For the simulation in MATLAB, we built an interface using the app designer that is built in, and we created an interactive interface with multiple panels and windows. It has an area where you can see the visualization of the projectile path, and one where you can input the data, which we can have like the intervals that it flows in, like the points that it maps out. And we implemented Euler's method to solve the projectile motion step by step. We set a time step of 0.01 seconds. We calculated the drag force at each step. We decomposed the drag into x and y components using velocity direction. And we updated those velocities, updated the positions. We did so by checking that y was positive, so it would not be lower than 0. So while the projectile was in the air, it would do those calculations, and then it would mark where it stopped. Here we can see a bit of the code that we made. And one of our many simulations that we did, we had to check a lot of the times. For the data types and structures, we used numbers for all the measurements. We saved the paths in lists. We added x, y positions at each step. We made some buttons and some sliders, which you can also type back the exact value you want. But if, for users that are like, for example, younger people, sliders might be easier to use. So we had that. We connected the buttons to the back end. We calculated the mass from the size since we can input the diameter. And for the visualization of it, we animated the path that it takes, which you can choose the intervals of how fast it goes. We painted the dots so it would look like lava. We showed live numbers. And then we also had to figure out how to add a volcano. I had this vector image that I had to draw. And from it, we had to figure out how to make it so that when the launch starts, like the volcano would be below it and also does not go below the ground. And so we had it like stretch and widen according to it. We also made a green line at 0 to show the ground, like it's a little bit of grass. And we marked where the projectile landed with an X. Yeah, here you can see like squished and taller.
For our final simulation, we have our simulation description, which is that the final simulation models the motion of volcanic projectile, considering both gravity and air resistance. Using Euler's method, the code updates the projectile's both position and velocity at every time step, calculating the drag forces in both the x and the y direction. Our code represents visually the parabolic motion that ends when the volcanic projection rock impacts the ground. As the activity requests us, the user can modify several parameters, such as projectile diameter, air resistance, or air density, drag coefficient, initial velocity, and initial position in x and y. Here you can see it in action. This is how our model works. You can see that the velocity and position is updating, and also you can see that you can change and modify the time intervals, so if you want it longer or shorter.
What we found from this was that air resistance greatly reduces the projectile distance, especially on ones that are much smaller. The projectile's not much closer to what our ideal calculations predicted and on our first simulator. Smaller projectiles are more affected by air. For example, 2 millimeter diameter projectiles travel much less than a 64 millimeter one. And we found that if you lower the angle, it reaches further. And 45 degrees angle, it goes the furthest of all, which is what we learned in physics class, so it's accurate to that. The initial velocity is important to the movement, since if you double it from 50 to 100, you can see it significantly increases the range, although we expected as much. I think the Euler's method worked well enough in our case. The simulation matched the expected physics behavior with small time steps, and when you use the small angles, it looks accurate to real-life volcanoes, which don't typically go higher than like 30 degrees. Here we can see our first simulation in Excel. You can see there's no air resistance, our very first model. And I tried to match the same values in our newest simulation. So using the same inputs as the first one, we put that in MATLAB to see how it would compare. And as you can see on our Excel simulation that we did at the start, it reached 107 meters of distance and a maximum height of 20.1 meters. Well, meanwhile, on our MATLAB, it only reached 98 meters in distance, falling short due to the drag. So since we have actual air resistance on this one and drag, it fell a little bit shorter than it. It would have gone a lot less if we had a smaller projectile, but we had a decently big one. What we could gather from these differences and running a few tests with different parameter values is this. One, air resistance reduces the landing distance by a sizable amount, meaning that actual danger zones are smaller than expected, and safety planners can use more accurate models to know what the impacted areas will be. We can tie this back to serious games since our MATLAB app shows how physics education can be entertaining and interactive. When you have like things like dials and sliders, it's more interesting and you can see the real-time feedback and immediate cause and effect. This can be expanded into much more full programs for volcano monitoring things or even like teaching students. For the real-world applications, we think that modeling movement helps predict where volcanic projectiles will land during actual eruptions. Since different projectile sizes can be tested in our program, you can see which would be the hazard areas, and authorities could use the simulation to plan evacuation routes.
In conclusion of our challenge, the project about developing a volcanic projectile simulation built in MATLAB App Designer by using methods like the Euler's one and including forces as the air drag or the projectile diameter that allows us to see a more accurate model. We learned that mathematics can help us to explain reality. Also, that it's really important that we know that this kind of games helps us to know how to act in these kind of situations that are important to our society. More in Mexico, that is a zone of volcanic it's a volcanic zone. And for further recommendations, we would like maybe to use some other tools for this, like maybe Python language.
Yeah, I think using MATLAB was definitely a challenge. I think it would have been a bit more enjoyable if we were using it on like a Python. There's probably some Python app like plugins that work similarly. The only thing I really liked about MATLAB was probably the app designer, but other than that, it was certainly a challenge to program the backend. But yeah, in general, I think it was a good learning experience.
Yeah.
Thank
Thank you for your
you.
attention.